an X such that the canonical is Neph. And we were in the middle of proving the non-vanishing theorem. If X is a minimal model, then some multiple of the canonical has a section. And our strategy was to basically derive a contradiction. So we said, suppose we had a minimal model X, but with Kodaira dimension negative infinity. Then, after playing around with some inequalities and the Albanese map, what we produced was a morphism alpha from X to an elliptic curve E with the property that alpha is smooth. So all the fibers are smooth curves, and the genus of the fibers are at least one. So that's where we were at the end of class. And then I stated this theorem that we're going to use to derive a contradiction. So I'll write the theorem a little more generally. Anytime you have a smooth alpha from X to E, smooth proper with fibers, curves of genus at least one, and so the genus of E is less than or equal to 1, so either an elliptic curve or P1. Then maybe I'll summarize it as alpha is isotrivial, but for our purposes, this will mean slightly different things depending on what the genus of the fibers are. So in the case that the genus is greater than or equal to 2, then this really means isotrivial in the strong sense that there exists some étale map T from E prime to E, so that when we pull back, then this alpha prime is really a product. Where T is étale or unramified. And then in the genus 1 case, we have a slightly weaker statement, which says that the relative canonical looks like it's a product. So in this case, we take the push forward of omega x over E, and then the claim is that this is a torsion line bundle. Which produces for us a cover where if we look at the same base change diagram, maybe x prime itself is not a product, but we know that the pullback of this line bundle which by some general cohomology and base change arguments is the same as alpha prime lower star omega x prime, is actually trivial. Again, where T is étale. Okay, so that's the theorem we want to apply. Okay, so let me give a very rough sketch of this theorem. So in the genus at least 2 case, the key point is that we have a moduli space of curves and that we understand its geometry. So we can take this as a black box, but basically we have this moduli space of curves of genus G at least 2. And at least complex analytically, this thing can be constructed as the quotient of some space Hg by a discrete group action, where this space is the Siegel, well, really this space sits inside of the Siegel upper half plane, but that's not so important. And this is a complex analytic quotient. But the important thing is that this Hg is bounded. It's some bounded complex domain, and it's also simply connected. This is the universal cover. And so if we have our smooth family alpha, x to e, then if you take as a black box that this moduli space exists, then we get a classifying map like this, depending on alpha, that sends e to the point in the moduli space corresponding to the curve in the fiber. But now, by some topology, this lifts the universal cover like this. And by, well, the universal cover is a local homeomorphism, so E tilde also gains a complex structure. And this map is E tilde to Hg is some holomorphic map. But now this universal cover is either C if E is an elliptic curve, or it's just E itself, i.e. P1, if E is genus 1. But either way, because the target is bounded, it's some bounded domain, there are no non-constant holomorphic functions that are bounded by like the maximum principle, say. So whatever this lift is the constant map. So so that tells us that at least if we pull back all the way to the universal cover of E, then we actually have a product. Because it's mapped to the moduli space as a constant map. But then we use that the automorphism group of a genus 2 curve is finite. And then by understanding the Galois correspondence between covering spaces, then we get that actually we just need to go to a finite cover to get a product. Okay, so that's a very, very sketchy sketch. And then the genus 1 case is essentially the same thing, except that we don't have a moduli space for genus 1 curves. We need to add a marked point, so we need to look at elliptic curves. And the point is that our original x to e might not have a section. So there might not be a way to pick out a marked point in every fiber. But we can take an associated fibration, the Jacobian, where we take the Jacobian of every fiber, and we can do this in families. And now this will be another genus 1 fibration where it does have a section given by the trivial line bundle. Since the Jacobian is the moduli space of degree 0 line bundles, the Jacobian has a distinguished point. And so this Jacobian fibration gives us a classifying map E to MG1. And again, this MG1 is the quotient of this time just the usual upper half plane by some group action. And so we can run the same argument to see that the Jacobian fibration is isotrivial in the strong sense. But this bundle, this push forward of omega, only depends on the Jacobian. Another way to say it is that this MG1 is really like the moduli space of Hodge structures. And so it's like we're taking, instead of looking at the actual elliptic curve without a marked point, we're looking at its Hodge structure, and that's what this classifying map is parametrizing. And that should, if you're familiar with Hodge structures, that's some of the significance of this push forward of omega bundle. It's the Hodge bundle, or maybe it's dual. Okay. Any questions about that? And I want to point out the reason that I wanted to use this particular idea instead of the more classical proof is I think this is the start of a really nice story about hyperbolicity of these moduli spaces. So this property that maps from a genus less than or equal to 1 curve are all constant. This is one way to talk about hyperbolicity in algebraic geometry. And positivity of these vector bundles of the form alpha lower star omega. And in the case of surfaces, this leads to a proof of a very famous conjecture, Itaka's conjecture. Which basically tells you how Kodaira dimension adds in fibrations. Anyway, so I thought it's interesting that this there's a lot of interesting things you can go from here. While like the classical proof does something completely different. The classical proof, basically, you have this alpha, and then you construct a different elliptic fibration on X using the fibers of this particular alpha. And there's some very clever but technical construction to do this, and then you derive a contradiction from the existence of this other elliptic fibration. Now we want to use this isotriviality to derive our contradiction, and our contradiction is just going to be that the Kodaira dimension is non-negative, because we assumed at the start that we had some surface that had Kodaira dimension minus infinity, then got to this point where now it's this isotrivial fibration over a genus 1 curve, and now we want to show that's a contradiction because any such fibration has some pluricanonical sections. And the point that, I'll write this as a theorem due to Itaka, back in the, I think in the paper where the Itaka dimension is introduced. Suppose we have some finite unramified map x prime to x. And everything's projective. Then the Kodaira dimension of x prime is equal to the Kodaira dimension of x. Okay, so now we can apply this in the genus greater than or equal to 2 case. Well, Kodaira dimension of x is the same as the Kodaira dimension of our trivial x prime. That's a cover, but since x prime is trivial, this is a product f times e prime. The genus of f is at least 2, and the genus of e prime, well, e prime is some cover of an elliptic curve, so that's at least 1. And so we have a product of curves of genus at least 1. So this has actually Kodaira dimension at least 1. And so that's a contradiction. And then in the other case, we compute with our push forward. So let's see. Yeah, let me draw this diagram again. We have our alpha prime. And now we know that T upper star, alpha lower star, omega x over E is alpha prime lower star, omega x prime over E, but is trivial by this isotriviality. And now we can push forward. Yeah, so now we want to find some sections of the canonical on x prime. So if we look at alpha prime lower star of the full canonical on x prime, not just the relative, then this is the pullback of the canonical of e prime, tensor this relative. That's the definition of the relative canonical. And now by projection formula, this is isomorphic to this bundle. But now this is O. So this is just omega e prime, and the genus of e prime we said was at least 1. And so H0 of the canonical on x prime because we're pushing forward, so they have the same sections, is equal to the genus of this base curve so the Kodaira dimension of x, which is the same as the Kodaira dimension of x prime, is non-negative because we have some section of the canonical. This was a typo. This should say kx prime. Okay, so in that case, we also get a contradiction. Okay, so that finishes the proof of non-vanishing. Are there any questions? Okay, so now we want to prove the abundance theorem. And recall the theorem was that not only does K have some sections, it actually has a lot of sections. So actually some multiple is base point free. Some multiple of the canonical. So the kind of the slogan for this theorem is that Kx nef implies Kx semi-ample. And in higher dimensions, this is a very big conjecture, probably the most important open problem in the field. Okay, and we'll see in the proof why it's so hard to generalize this to higher dimensions, because the proof is basically case-by-case work. Once we have non-vanishing, we know there exists some section, and then we do case-by-case work to check that for every numerical possibility, Kx is really semi-ample. And there's this abundance is known in dimension 3 as well, and again, the proof there is the same. There's just more cases. Well, I won't say that the cases aren't, the proofs of the individual cases aren't the same, but the fact that you have to do a case-by-case analysis is still the same in dimension 3. Okay, so by non-vanishing, we know that the Kodaira dimension of x is non-negative. So now we just check all the different possibilities. If the Kodaira dimension is 2, so this is the general type case, where the dimension is equal to the Kodaira dimension. This is the case that actually works uniformly in all dimensions. And here it's a corollary of a much stronger base point freeness theorem. So we talked a little bit about the base point free theorem when we were studying surfaces with Kx not nef, and trying to produce these extremal contractions that contracted Kx negative curves. Here we'll need an even stronger version than the one stated there. I want to give just a vague statement of it, since we'll prove the full thing later on when we move on to higher dimensions. So suppose x is a smooth projective variety, and D is a divisor. So some linear combination of prime divisors DI. Let's suppose that these coefficients are rational numbers, but they're between 0 and 1. And then let's say that the singularities of D are nice, which I won't define now, but we'll spend a long time talking about the various singularity properties later. Then if L is some Neff Cartier divisor, such that the difference AL minus KX plus D is ample for some A, then L is base-point free. Or L is semi-ample, I guess. Then some multiple of L is base-point free. Okay, so that's the one slight generalization of the base-point free theorem, not the most general version. This nice condition is that the pair has KLT singularities, which we'll define in a few weeks. Okay, so that's all I'll say about this general type case for now. Maybe I'll also say that just with everything else, you can also prove this directly for surfaces. If you do a careful analysis of the types of curves that can appear on these general type surfaces with KNF, and you can kind of construct the image of this base-point free map, and then check that it really is this particular linear series. You can kind of go backwards. Okay, so now we have Kodaira dimension 1. So in this case, by our numerical characterization of bigness for Neff divisors, so this is the case when kx squared is 0 because it's Neff but not big. But k itself is not 0 numerically. Because we know we have our growth rate of sections is positive. So this kind of condition, there's a notion of numerical Kodaira dimension. And this is a condition that says that the numerical Kodaira dimension is 1 because 1 is the first power where it's not numerically trivial. Okay, so in this case, let's look at our MKX, which is non-vanishing. So we have some M where we actually have sections. And let's write this as M plus F, where this linear series, so M is some divisor, and this linear series of M is the moving part of MKX. And this linear series here is the fixed part. So basically what this means is it might be the case that there's some divisor F, which is contained in every section of MKX. Pull that out, that's going to be F. So every section of MKX is of the form F plus something linearly equivalent to M. And we know that this M piece is not empty because the Kodaira dimension is 1. So we know that the growth rate, like for large enough M, we know we have more than one section. So it can't just be a fixed divisor. Okay, so write it like that. And now we'll do some computation. So we know that 0 is less than or equal to m squared. And the reason is because m is moving. That m doesn't have any fixed component. And so when you intersect it with itself, you can take m and you can take something linearly equivalent to m that doesn't share any components. Then the intersection is some finite collection of points with multiplicities. So either way, you get a non-negative number. So m squared is greater than or equal to 0. And in fact, we know a little more. We know that m is actually nef. Again, any moving divisor has to be nef. Okay, so we have 0 less than or equal to m squared, and this m is actually nef because it moves. And now this is less than or equal to m dot m plus f using this nef property of m. Actually, even easier here using that f is not contained in any component. Like the components of f and the components of m have to be different because of the way we split up our divisor. So m dot f is greater than or equal to 0. So this gets even bigger. And then this is less than or equal to m plus f squared. So here we're using that m as nef. And then m plus f is just our divisor k. So here we have mkx squared. But kx squared is 0, so this is 0. So this tells us that m squared equals m times f equals f squared are all 0, the string of inequalities. Okay, so now we have this moving divisor m. That satisfies m squared equals 0. But that exactly means that if we have two linearly equivalent divisors in this linear series, they can't intersect at all because they don't contain any components, so their intersection is greater than or equal to 0. And if they had any points of intersection, you'd get a strictly greater than 0 intersection. So once we know we have a moving divisor whose square is 0, then it actually has to have no base locus, i.e. m is base point free. So we have some morphism corresponding to m. And we know that its image is a curve because the growth rate of this of the sections for m, the Kodaira like the Itaka dimension of this m has to be the same as that of the canonical because it's because the canonical linear series is like m plus this fixed part. So they have kind of the same growth rate for sections. So this has to be a curve. And now we use this lemma from the Hodge index theorem because we have this f satisfying two things. One, it satisfies that f dot m is 0 from the string of inequalities here. So that implies that f is contained in a fiber because we have a base point free linear series. But on the other hand, we also know that f squared is 0. And so by this corollary of the Hodge index theorem, that implies that f has to be a multiple of just some fibers. So f has to be of the form sum of some mi fi, where the fi's are fibers of phi. So this was by Hodge index theorem. But now that tells us that our canonical, or m times the canonical, which was m, or linearly equivalent to m plus f, is the same as phi upper star of an ample on Z, because we have the space point free linear series. Just the definition of linear series means that M is the pullback of an ample, plus sum of Mi times phi upper star of a point on our curve, because now we have these sums of fibers, but this whole thing is just phi upper star of some divisor Hz plus some Mi Pi, which is just a different ample on a curve. And so we have this divisor that's the pullback of an ample divisor by a morphism, so it has to be base point free. Basically, what this is saying is that the linear series associated to m plus f has to just be the thing you get when you take your z, that was the target of the linear series of m, and re-embed it into a different projective space using this other ample divisor, and then that's the linear series for m plus f. Either way, it's still base point free. Okay, so that finishes the Kodaira dimension 1 case. Any questions? Okay, and now the most involved one is the Kodaira dimension 0 case. Okay. So now we have our Kodaira dimension 0 case. So in this case, what this means is that the global sections of any multiple of the canonical are at most 1. That's the definition of being Kodaira dimension 0, essentially. In this case, we also know that the Euler characteristic of O is greater than or equal to 0. This was one of the lemmas we proved last time, that if you have a surface with Neff canonical bundle of Kodaira dimension less than or equal to 0, then the Euler characteristic of O is at least 0. This was a lemma. And then this tells us, so this is 1 minus H1 of O plus by duality H0 of OX of KX. So this is greater than or equal to 0, but also this term is less than or equal to 1. And so now we can go through the possible cases. There's essentially only five possibilities for what H1 of O and H0 of K can be. So we can have, and let me write down the notation for these. So this was, I guess there's two pieces of notation for H0 of O of K. You can either think of it as the first plurigenus or what's just called the geometric genus. And then this was this irregularity. So this is geometric genus. And this is irregularity. Okay, so let's write down our possible cases for Q and PG. So we could have both of them 0. We can have PG 0 and irregularity 1. We could have PG 1 and irregularity 0. both of them 1, or PG1 and irregularity 2. So those are the only cases allowed by these inequalities. And each of these have a name in the classification. So let me write down their names. This first case is an Enrique surface. And these you can think of as definitions, but we'll describe the structure of the surfaces you get in each of these cases as well. But if you want, you can just think of it as a definition. An Enrique surface is a Kodaira dimension 0 surface with kx nef and with these numerical conditions. Similarly, the second one is what's called the bielliptic surface. The third one is a K3 surface. The fourth one actually just doesn't exist. And the fifth one is an abelian surface. Okay, and to prove the abundance theorem here, we just have to go through every case and check. Well, what do we have to check? So in this Kodaira dimension 0 case, if we do have a base point free linear series, then it's just the map to a point. So this tells us that so abundance is equivalent to the statement that m times kx is pulled back from a point, but that means that m times kx is just a trivial bundle. So what we really have to check, or the trivial divisor. So essentially we need to check that m times kx is linearly equivalent to 0 for some m greater than 0. That's equivalent to abundance in Kodaira dimension 0. And in each of these cases, it'll be a different argument and a different m that you'll need to take, or a possibly different m. A few of them are the same. Okay, any questions before we start that? Okay, so in our first case, so this is PG equals Q equals 0. We know Castelnuovo's rationality theorem, which tells us that if furthermore the second plurigenus was 0, then X would be rational, but it's Kodaira dimension 0, so it can't be rational. So this tells us that we have a section of 2K. Okay, and now, right. So now we want to show that 2K is actually trivial, or is linearly equivalent to the 0 divisor, and that's the same as saying that 2K and minus 2K have sections. If you have a divisor D so that both D and minus D have sections, then it has to be linearly equivalent to the trivial divisor. So we want to check that H0x OX minus 2K also has sections. And so we'll use some Riemann-Roch to do that. And then this would immediately imply that 2kx is trivial. Okay, so to do this, let's just write down Riemann-Roch. So H0x OX minus 2kx minus H1 plus H2 I didn't include the minus term, so this is all greater than or equal to what Riemann-Roch tells you. And I should have written here, what's the Euler characteristic in this case? Well, the Euler characteristic in this case is 1. So in each of these cases, we also care about what the actual Euler characteristic is because of these Riemann-Roch computations. So if we plug in, this is 1. This term is 0 because k squared is 0. And this term here is the same as h0 of OX 3kx, which is less than or equal to 1. And now here's an exercise. If you have both h0x 2kx is 1 and h0x 3kx is 1, then this would imply that just kx is 1. That's an exercise. Essentially, you know that you're assuming that they both have unique sections, and then you check that they share a component, so that there's some section in just 1 kx. Okay, so that'll leave as an exercise, but this isn't the case. We know we're in this case where PG is also 0. So we know that, sorry, I meant to say 1 here. So we know that this is not 0. Sorry, this is not 1. We know that h0 of OK is 0. So we can't have both of these terms. Sorry, we can't have this term and this term. We can't have both this and this be equal to 1. So this implies that h2x OX 3kx is actually 0. And so then this goes away, and we get that h0 of O of minus 2 is at least 1. Because the Euler characteristic is 1. So 2 and minus 2 kx both have sections, so they're just the trivial bundle, or the trivial divisor. Okay, so that was the Enrique's case. So we can add to our table if we wanted that in this case 2k is trivial, and this will be important later. Okay, next one, we have PG equals 0 and Q equals 1. So in this case, the Euler characteristic is 0. And now we use the Albanese map. So now we have an Albanese map x to E, where E is an elliptic curve. Again, because Q is 1, so we know that the Albanese variety is one-dimensional, so it has to be an elliptic curve. And now we basically run the same argument that we did in the proof of non-vanishing. So then this tells us that alpha is smooth. And the genus of the fibers is 1. Well, I guess we want to deduce that, but a priori it tells us that alpha is smooth and the genus of the fibers is at least 1. That was the argument that we already wrote down in that previous proof. And now we also know that some cover So in the genus greater than or equal to 2 case, we have that this is a quotient of some E prime cross F where the genus of F is greater than or equal to 2, but that's a contradiction because then the Kodaira dimension of X prime we have a genus at least 0 curve E prime, and then we have a genus at least one curve E prime, and a genus at least 2 curve F. So the Kodaira dimension here is greater than or equal to 1, but we're in this Kodaira dimension 0 case. So this can't happen. So that's how we know that actually this Albanese map has to be a genus 1 fibration. But then in this genus 1 case, we again use the same argument that omega x. Yeah. So we know we're in this genus 1 case, and then we look at omega x is alpha upper star omega e tensor the relative. I see. Sorry, this is relative duality. We get that this is R1 alpha lower star OX dual. This is the same as, so okay, omega E is just O, and omega X by the canonical bundle formula is just the pullback of this R1 alpha lower star OX dual. Basically, I'm running through the proof of the canonical bundle formula, in this case, kind of accidentally. But basically, because all the fibers are smooth, then the canonical bundle formula will tell us that this pullback push forward of omega is just omega, and this is 0 because E is an elliptic curve. And so omega x is the pullback of this push forward of omega x over E on the elliptic curve. But then this moduli argument told us that alpha lower star omega x over E is torsion bundle on this E. So that implies that some power of this line bundle is trivial. And so when we pull back, we get that some power of omega because alpha upper star is compatible with tensor products. Is also trivial. Okay, sorry I butchered that a little bit. Okay, so here, this case is essentially the same argument we already used in the non-vanishing, except we're not deriving a contradiction because we're not assuming that the Kodaira dimension is minus infinity. Okay, and here we don't know yet what M is, but once we finish the classification, we'll go back and we can see how you can figure out the possible M's and what the structure of these surfaces actually is. Okay, so then the third case, this is the case where the genus is 1 and the irregularity is 0. And in this case, the Euler characteristic is 2. Oh, and I should say actually here, M can't be 1. So the one thing we do know is that M has to be strictly bigger than 1 because the genus is 0. So Kx itself can't have any sections. Okay. Okay, so now we're looking at PG equals 1 and G equals 0. In this case, the Euler characteristic is 2. So here, we're going to see that actually K itself is trivial. So we're going to run the same type of argument where we want to show that both K and minus K have sections. So we know K has sections because PG is 1. So we're assuming K has sections. And so we want to show that minus K has sections. So we write down Riemann-Roch, we get H0 of O of K plus H0 of O of 2K is greater than or equal to, again, the first term is 0 in Riemann-Roch because we just have the canonical and we know that Kx is squared. So we'll get 0 plus the Euler characteristic of O, which is 2. So we know that H0 of O minus K plus H0 of O 2K is at least 2. But on the other hand, we also know that H0 of OX of 2KX is at most 1 because Kodaira dimension is 0. So we know that the growth rate of sections is constant. So that tells us that H0 OX minus K is at least 1. So Kx is trivial because it has a section from the genus being 1, and it's minus K also has a section. So it's just trivial. So this was the K3 case in the naming. Okay, so let me go back here and add this. So here, so far, we just know that MKX is trivial for some M greater than 0. And here we know that in the K3 case, KX is actually trivial. So the last two cases, we want to show that this PG equals Q equals 1 case doesn't exist, and that this last case is an abelian surface. So in this case, the Euler characteristic of O is 1. And now we can write down this exponential sequence for Picard. I think I did this a few classes ago, where we get that pic 0 of x is the same as h1 x ox modulo the image of the connecting map from h1 x z. So this was from taking cohomology for this sequence. But now we know that Q is 1. So we know that this pic 0, this Picard variety or Picard group of X is one-dimensional. So this is not 0 because Q is the same as H1XOX, which is the same as the dimension of Picard. Okay, so now we have this pic 0 of X, which is a quotient of some complex vector space of dimension. Oh, I guess you can even just see it here. H1XOX is 1. So it's some complex vector space of dimension 1 modulo some lattice. So this is some genus 1 curve. And so we can pick a 2 torsion line bundle that's not trivial. So just pick some M in pic 0 that's 2 torsion but not trivial. So basically pick some point in H1XOX, so that 2 times that point is in the image of H1XZ, but the point itself is not in H1XZ. And now, because it's not trivial, it's torsion but not trivial, then we know that H0 of M is 0. But on the other hand, let's compute with Riemann-Roch. So H0 of, okay, so we have this H2 term in Riemann-Roch. This is greater than or equal to 1/2 m minus k plus chi. But m is a torsion line bundle, so it's a multiple of 0, and the intersection product is linear. So m itself has to be numerically trivial, because 2 times m intersects everything to be 0. So this whole term vanishes. And chi of OX we set up here is 1. So that's 1. So that tells us that kx minus m has a section, because h0 of kx minus m is greater than or equal to 1. So pick that section, some g in kx minus m. Then 2g will be an element of 2kx minus 2m, but m was 2 torsion, so this is just 2kx. So we have some g, so that 2 times g is an element of 2kx. But on the other hand, we're also assuming the genus is 1, so we also have some d in just kx. Kx is a unique section given by some d. But because this is unique, and we can check that, let's see, OX of 2kx, well, this is less than or equal to 1 by Kodaira dimension considerations. So we know since D has a section, since kx has a section, then this is actually exactly equal to 1, because we just take 2D. It's actually equal to 1. And this tells us that the linear series 2kx contains the unique divisor 2D. So 2D has to be the same as 2g, because we found a different divisor 2g in this linear series. But now we just get a contradiction, because kx is linearly equivalent to d, which is equal to g by this equality, which is linearly equivalent to kx minus m, which would imply that m is linearly equivalent to 0. But we picked m that was not linearly equivalent to 0. Okay, so this case just can't exist. Okay, so that leaves our last case. Hopefully I can get it done in 4 minutes, where PG is 1 and Q is 2. And so in this case, the Euler characteristic of O is 0. And now the key point again is to use the Albanese, because we have this Q2. So we know we have a big Albanese map. So we have some x to Albanese of x, let's call it A, where A is 2-dimensional. So this is some abelian surface. So the first claim is that this alpha doesn't factor through a curve. Okay, so suppose it did. Then by this universal property of the Albanese, we would have that the genus of C is 2, and that A is the Jacobian of this C. Right, but on a genus 2 curve, there exist étale covers of large degree. So pick some T prime from C prime to C, where this is some étale cover finite étale cover with the genus of C prime strictly bigger than 2. These exist for higher genus curves. And now take the pullback. So when we take the pullback, we get an X prime going to C prime, and then composing to the Jacobian of C prime, which is the Albanese of X prime, which is dimension at least 3, because the C prime has genus at least 3. But on the other hand, because C prime to C is étale, then when we take the pullback, X prime to X is also étale, so the Kodaira dimension of X prime is the same as the Kodaira dimension of X, is 0, but its Albanese is 3-dimensional, so the Q of X prime is 3, and that wasn't numerically possible by our inequalities. Okay, so no such X prime exists, so this alpha has to be dominant. So can't factor through a curve. Okay, and now once we know that alpha is surjective, that means that it's generically finite. And now we can write down the Riemann-Hurwitz formula for the canonical divisor, which essentially in higher dimensions, it just says that if you have an unramified map, the canonical pulls back to the canonical. And so the difference between the canonical and its pullback is exactly the ramification of the map. Or to put another way, Kx is alpha upper star Ka plus some E, where E is some effective divisor, but it's the ramification divisor. But the important point is just that it's effective.